I have a question.
Sure.
For part two, when we're supposed to have the better multimeter measuring the current between point A and C,
Yeah.
we have to use the other multimeter to measure the current through, measure the current for battery, right?
Well, yeah, you're going to have to do it that way. Yeah.
I was just, I could like switch the multimeters, but I thought it would kind of ruin the experiment because I wouldn't know what exactly would be the current through battery when I'm using the better multimeter for A and C.
The reason why
So
I
I'm just,
go ahead. I'm sorry.
I was just wondering if I have to use the other multimeter to measure the current through battery.
Yeah, because you need to have you always have to have a meter between points A and C. I mean, you can switch them if you want. I haven't tried switching them, but I figured that the good one has an extra sig fig when you're measuring a small current. Although it's true that the smaller meter actually has a lower current scale. There's a 200 milliamp scale and a 2 milliamp scale. I mean, you can try switching it and see what happens. All it's going to do is affect sig figs.
Yeah, I just realized the other multimeter actually has a milliamp scale. I didn't actually know.
There's a microamp scale too,
Yeah, yeah,
but
yeah.
yeah,
Sorry.
if you can switch them, try it.
Okay, thank you.
Sure. The problem with this lab is that you have two different multimeters because if you were on campus, there was no, you'd only have one type. And now this becomes a question, which one do I use for what? So you can switch them, that's fine. Just let me know. In fact, it's a good idea, you write down which meter you use for measuring IAC. Because you got to keep that there the whole time you're making all the measurements. Because by putting the meter across AC, you completely change the circuit compared to part one. Because what happens is point A and point C now are at the same potential.
Okay, how do I let you know that I'm using like the better multimeter?
You
Do I
can write
just
it below. You can write it underneath the table.
oh, okay.
I mean that would be fine. Are there other questions? Has anybody done all the measurements yet?
I think I'm almost done.
The results
It's
come out
just
okay?
yeah. It
Okay.
wasn't well. I haven't done any analysis on it yet. I wouldn't know, but the results seem just fine.
I mean, because like when you measure, like for part one, if you do I1 plus I2, is it equal to IS? Or is it
Yeah, I
close to
haven't
it?
done that yet.
Okay, you have done the calculations.
No.
Okay. Anybody else? This is the time where you can ask questions if you're having trouble. Otherwise, you have to, make an appointment or come to my office hours. No other questions? Okay. And maybe something will come to you as I talk here. A couple of things I didn't say, I didn't talk about last time, so I want to say them now. So let me go and switch my, actually, let me go this way. You notice that, resistors come in different sizes. And there's a reason for that because resistors have power ratings. So if you build a circuit, let's say like this. And I'll put the meter here just for fun. Let's say you design a circuit, and all your resistors, they can be like this, or you can get a real big one like that. The fact that they're different, they represent different power ratings, so different size. So resistors reflect different power ratings. Okay? So you can have resistors that are a quarter watt, actually an eighth watt, 8, half watt, 1 watt. The higher the rating, the bigger the resistor. And you have to pay attention to the wattage rating, because if you have a quarter watt resistor and you set up your circuit and at some point you go over a quarter watt, what's going to happen to that resistor? Well, first of all, it's not going to behave like an Ohm's law resistor. It's going to get warm. And if you put too much current through it, if you go way beyond a quarter watt, it'll start to smoke. Okay? So these power ratings are important. And I think the resistors you have are either, I forget, quarter watt or eighth watt. Okay, so you have to be aware of not putting too much current in them. And in this lab, it's not a problem. But normally, if we were doing this lab on campus, instead of setting the power supply to 6 volts, what I would ask you is this. I would say, okay, I'm going to give you a power supply. Find the maximum voltage you can apply to your circuit, and then do it. Use that maximum voltage. That's what I would have you do. So if you calculate the maximum voltage you can apply is 18 volts, I would expect you to set the power supply to 18 volts. Okay? And so in order for you to figure out what is the maximum voltage you can apply, you got to find out which resistor is your weak link in your circuit. Which one is going to be the first one that's going to go over the rating. I don't know if you remember, there's a problem in chapter 26 with capacitor bank, and you had to find what is the maximum voltage you can apply to your capacitor bank so that none of the capacitors get blown. The same idea. And you can always use the equation P is equal to I squared R, or P is delta V squared over R, to figure out, what you should be able to apply in your circuit. Usually you use this one if resistors are in series, and this one if resistors are in parallel. Right? You set this to the power rating of the resistor, and then go through. That would be like a good exam question, wouldn't it? Okay, so I wanted to mention that because we're not doing that in this lab, but I mean, normally when we're on ground, we all do that because it's important. Design consideration. By the way, what I have on the board is not for you guys. So, okay. So I erased that. When you're doing this part, let me find my circuit. and you have to measure the current across AC, what I would do, and I'll put this up on the screen, I'll put this up real close. I don't know if you can see the red and the black wire. I would have the red and the black wire sticking out like that, and then tape the leads of the meter you're using to measure the current to keep it in place. That would be the easiest thing to do. Okay. And I know these wires are a little stiff, but they're actually okay for this. If the wires weren't stiff, they wouldn't work well for the breadboard. Remember, there's the electrical tape that comes in your kit. It comes with there's a motor kit. One of the labs we're going to do, and I'm going to introduce next week, is called the DC motor. And there's a kit that you were given, and inside there, it's in a bag. Inside the bag, there's electrical tape. So you can use that electrical tape. You don't have to use your own. Okay. Don't forget, you're going to be doing a lot of air propagation. So when you measure I1 and I2, and you calculate IS is I1 plus I2, then delta IS is going to end up being the square root of, and I'm doing this very quickly, okay. These are things I might have omitted last week that I'm mentioning now. Please don't hesitate to ask a question. Some of you folks have asked questions. I had one student, I don't think it was in this class, but they had their multimeter wasn't working. They blew a fuse. So if you blow a fuse, the fuse is easy to find on these things. I mean, when you open this up and look where the battery's at, the fuse is right next to the battery. Okay, and you can replace the fuse quite easily. As you take the old one out, put the new one in. It just snaps in place. And I think on the smaller one, it's beneath the battery. Okay, so if you don't have any more questions, I want to talk a little bit about. Actually, I want to finish up what I was saying about force on the wire, and now talk about torque and the electric motor. Just give me a second here. So, actually, last time in lecture, Friday in lecture, we talked about the force on a wire in a magnetic field. And so, for a wire in a uniform magnetic field, the force on the wire is the current in the wire times L cross B. Where L is, for a straight wire, L is the length of the wire. But if the wire is curved, then L is basically the distance between the two endpoints of the wire. Or it's the magnitude, and it's the vector that points from one point to the other on the wire in the direction of the current. If you have a magnetic field that varies, then probably what you're going to have to do is calculate the magnetic force on a small element of the wire and then integrate over the whole wire. Your worksheet is based on this. And then the last problem I did in class the other day was based on this. So I had a little question for you. given this scenario, you have a horseshoe magnet and you have a current carrying wire, and you want to determine which is the North Pole and which is the South Pole of the magnet. Remember that magnetic field lines go from the North Pole to the South Pole. What do you think?
The left is the South Pole?
I'm sorry?
The left is the South Pole?
Yeah, it turns out the left is the South Pole. So let's take a look at why.
Is that just like a right-hand rule sort of practice thing, or is that like...
It is a right-hand rule.
Right? Oh, yeah.
Because this is a cross product, right? It's the same right-hand rule. I mean, I didn't really say much, but it is a right-hand rule. But in this particular case, the right-hand rule is written in terms of you point your fingers in the direction of the current, and then curl them towards B. So let me draw a coordinate system. Let me draw it in black. So our current is this way. Our force is up. By the way, question about this direction of current. Are we talking about conventional current flow or charge flow? Actually, it doesn't matter because I depends on the product of Q and this vector. So for electrons, these both change signs. It doesn't matter. Okay, and we're given that the force is upward, I is into the board. So I gotta, and really I'm gonna have to just guess. If I guess that the magnetic field is this way, and if I use the right-hand rule, let's see, I point my fingers in the direction of current, and then I gotta curl them towards the magnetic field. How am I gonna do that? I'm going to have to go, oh, here we go. I'm going to curl in the direction, I'm going to curl towards the magnetic field. My thumb points downward. Okay? My thumb points downward. But if the magnetic field is this way, I point my fingers in the direction of the current, curl them towards B. My thumb is up. So the magnetic field is that way. The magnetic field lines go from the North Pole to the South Pole. So this would be the North Pole, that would be the South Pole of the magnet. That makes sense?
Yep.
Okay. Application of magnetic fields as a loudspeaker, and I didn't bring my loudspeaker in. So you can, if you take a coil of wire, also known as a solenoid. Darn, I didn't bring it with me. And you take a paper cup. So you take a coil of wire. I'm going to have to demonstrate that for you. and you put a paper cup with a magnet in it, and you put an alternating current, you can get the cup to vibrate, make a sound. And that's essentially what a loudspeaker does. Although it's a little bit more sophisticated than what I just said. So you have, in this particular case, a loop of wire in a non-uniform field. It's not a uniform field. So there's a permanent magnet back here. So you have the coil of wire, the black, hold on a second, let me magnify that, sorry. The little black circles represent the coils of wire. They're in the magnetic field. This field is non-uniform. And if one does a calculation, and really I'm just focusing on the here I'm just focusing on the application, but if one does a calculation for this cardboard, it's a special cardboard for speakers, the maximum acceleration of a cone at a particular instant can be as large as 43 meters per second, which is 4 Gs. So when you have the current that's going in here varies with time, it's the AC current. Okay, and so it's going to cause a loudspeaker to move back and vibrate back and forth. It's going to cause the vibration. The vibrating causes the air molecules to vibrate. Question?
Oh, I was gonna say, so the current then induces a magnetic field, or there is a magnetic field.
There's a permanent magnet, and the fact
Okay.
that current is in the magnetic field. But this is not a uniform magnetic field.
So like the current varying is what creates the vibration because it changes the direction of the force?
Correct.
Okay.
Yeah. Okay. Oops. Yeah, so let me just say something about putting a magnet in a non-uniform field. Let me give you a quick example. Suppose you have a bar magnet. It's going to be hard to draw. Suppose you have a bar magnet. And they have some sort of coil. Let's do it this way. In the bar magnet. I don't know if that's a good drawing. Of course, the field due to a bar magnet will look like this, right? And at any point on the coil of wire, there's going to be a component, it's going to experience a component of B that points upward and a component of B that points outward. Same thing here. It's going to experience a component upward and a component outward. Now, what did we say about a uniform magnetic field? We said that if you have a wire in a uniform magnetic field and it forms a closed loop, it's not going to experience a force. So this is a closed loop. So the components that are vertical, the vertical component from the north side of the magnet, that part is uniform. And so if you integrate all the way around the loop of wire, the force due to the vertical component of the magnetic field will be 0. But the horizontal component constantly changes direction. And so this component is not going to be 0 because as you go all the way around, it changes directions. And so that component will give you a non-zero force. Basically, your dl will be rd theta. So basically, you're going to have I times b times the circumference of the circle. So basically, if you do this particular case, your force will be the circumference of the circle okay, times I times B. Because your dl is r d theta, at least for the horizontal component, because it changes direction all the way around. It's not uniform. Okay, and that's how this speaker works. The horizontal component of the field cancels. The force due to the horizontal component cancels, but the force due to the vertical component does not, because that one changes directions. Okay. So now I want to talk about the torque on a loop of wire in a magnetic field. So imagine you have that black loop of wire in a magnetic field. There's four sides to this loop. Let's say the current is going clockwise around this loop. Okay, so we have a clockwise current going around this loop. Excuse me. If you look at the top loop, if you look at the loop at the top, the current is pointing from left to right. And in magnetic field, it's from left to right. What is the force on that top wire? Zero. Let's assume the magnetic field is uniform. So the force on the top loop is zero. The top part of the loop is zero. Similarly, the force on the bottom part of the loop is zero, because the current is either parallel or anti-parallel to the magnetic field. But what about the vertical parts of the loop? Focus on the left one. There's going to be a force on the loop into the plane of the page. Use the right-hand rule. And there's a force on the right vertical wire out of the plane of the page. The sum of the forces equals what? If the field is uniform, the I is the same.
Zero.
Zero. But the sum of the forces is zero, but those forces are going to make that loop want to rotate. Because if you sum the torques about the center of the loop, both forces are going to produce a torque. If you look from the top, if you look from above the loop, both of them are going to cause a clockwise torque. So if you look from the top, and that's this figure on the lower right, this is a view from the top. Both of those forces are going to cause a rotation that's clockwise. And if you use the definition of torque, I'll write it up on the board. Torque is R cross F. Or the magnitude of the torque is the magnitude of R times the magnitude of F times the sine of the angle between them. Okay? Well, let's look at the torque produced by the force on the left. Okay, so let me draw the picture. You have a force this way and a force downward. Let's call this phi. So maybe I should call this phi. Okay. And let's sum the torques about the center of the loop. Okay. This is the width of the loop. So this will be W over 2. This is W over 2. Okay. Now the force on the vertical loop is ILB. We're looking at the case where I is perpendicular to the magnetic field. So we know F is going to be ILB. The sine of 90 is 1. So I'm going to do, our R is this guy, the distance from the pivot point to where the force is being acted at. RF is ILB. And then the angle is phi. And then I can do the same thing for the other force. And you can see that the other force is going to produce the same torque. So instead of adding plus so and so and so, I'm going to multiply by 2. The 2's cancel. This is the length times the width of the loop. What's length times width? The area.
Where'd the 2 come from? Sorry.
Okay, so this would be a phi, not a theta. So you agree with me that the torque due to this force is given by this expression.
Oh, I see now. Okay.
And then the other one's the same thing, right? So this is the torque on a loop of wire. Okay. This is the angle. Now we got to be careful here. This is the angle, phi is the angle between B and the normal to the loop. That's how we define phi. We don't define it in terms of the force. We define it in terms of the normal to the loop. Okay, phi is the angle between B and the normal to the loop. You can see it in the figure. You okay with that? And the torque is perpendicular. The torque is perpendicular to R and F. Where would this be applicable, making a loop of wire turn? Where would this be of use? To run a current through a loop of wire. Oops, let me go back. Running a current through a loop of wire that causes a torque on that loop of wire. Where would be a good application of that? Where would you use that?
A motor?
On a motor, yeah. So I'm going to talk about a motor in a minute. Now, my equation for the torque is for one loop of wire. But a lot of times you have many loops of wires wrapped. Okay, instead of having one loop, if you notice on a motor, you have many loops, right? So if you have n loops, then this equation has to be multiplied by n. This torque is perpendicular to this guy. And the normal to the loop. So we can rewrite this as a cross product. We can write it in the following way. And this area vector basically is the normal to the loop. You might say, well, okay, I have a loop of wire. What's the normal to the loop? Aren't there two normals? If I have a plane, if I have a sheet of paper like this, aren't there two normals to this piece of paper? Is one this way and one pointing in the opposite direction? How do I know which one do I choose?
Right hand rule.
Right hand rule. You curl your fingers in the direction of the current. Okay, you curl your fingers in the direction of the current. And that'll give you the correct normal. That'll give you the correct direction of this guy. This is called a magnetic moment. And usually we don't introduce where this comes from in an introductory class, but later on you'll see where this comes from. Okay, if you take a more advanced course. But we call this the magnetic moment. And yeah, the direction, the normal to the loop is by the right-hand rule, determined by the current. You curl your fingers in the direction of the current, your thumb points in the direction of the normal. So a lot of times we use either the Greek letter mu or m for the magnetic moment, but it's m cross b. And in introductory courses, you only do torques on loops in the uniform field. Doing a torque on a loop in a non-uniform field is a bad problem to do. We don't do those. Okay. So this video is going to cause me problems. I'll try to play it later. So here's an example of using the idea of a torque in a loop. It's an ammeter. It's the old ammeter analog. So you have a magnet. Oops, let me change the view here. You have a magnet. And then when you're measuring the current in the circuit, you have a loop of wire. Current runs through the loop of wire. And because it's in a magnetic field, it's going to cause it to rotate. You have the spring at the top to produce a resistive force so it doesn't rotate as much as, otherwise it's going to rotate continuously. This spring makes it rotate up to a certain value. So you have to calibrate it, right, based on this scale. So you have a loop of wire in a magnetic field, the spring produces the resistive force so that the thing doesn't keep spinning around. And this is the way, in the old days, you measure the current. And everything's done with solid state equipment. So I want to talk a little bit about the motor. I'm going to introduce the lab next week. It's really more of a project. You all have a motor kit. And so next week, I'm going to tell you about how to build this motor. Well, it's actually not hard to build a motor. What's hard is to make it work for a certain voltage. So we'll talk about that next week. But a DC motor converts electrical energy into mechanical energy. It's a generator that's actually working backwards, if you can think of it that way. Okay. It's basically a current loop in a magnetic field. And I have a motor here. I'll show you the motor in a minute. There's three main parts of the motor. There's an armature, which consists of a coil of wire mounted on a cylinder. In your case, it'll be more like a cylinder, but your cylinder in your lab is going to be made of two nails. Okay? And the armature is what does the mechanical work. The armature is what transfers energy from the system to the environment. And then there's brushes and commutators. The brushes are stationary contacts that rub against the commutator. And it transmits the electrical energy to the armature. For a DC motor, the purpose of the commutator is to reverse the direction of the current when the loop of wire rotates 180 degrees. Because what happens is, if you have a loop of wire in a magnetic field, If you have a loop of wire in a magnetic field, when this thing rotates by 180 degrees, then when the thing flips 180 degrees, if you don't reverse the direction of the current in your loop of wire, then the torque is going to be in the opposite direction. So your motor is just going to oscillate back and forth. It's going to be completely useless. Just imagine when this thing flips 180 degrees, what happens? The torque will reverse direction, and then you're going to have the basically a no net torque in one cycle. Okay. All right, so let me show you a motor. I have one with me. Let me see if I can zoom in a lot on this motor. Can you see this okay? Otherwise, I'm going to have to pick it up and bring it real close to the camera.
It's kind of blurry, but
It's a little blurry because I magnified
yeah.
the heck out of it. Let me see if I can reduce. How about now?
That's not bad.
I'll make it a little bit less. Yeah, I might have to pick this. I might have to pick this up. That means I have to disconnect everything. It's really heavy too. I'll take it apart. That's fine. Okay. You see this okay?
Yeah.
Okay. So, this is heavy. This is the armature. Okay. This is the armature, basically this part that turns. There's a coil of wire. That's the armature. The bottom part here is the electromagnet. And then on top of here is your, oops, wrong way. This is the commutator, and then these little things are the brushes. Hopefully you can see that. I don't know, we'll see. So, when I apply a current, and I got to connect everything again. Just give me a second. One. So I'm doing two things. I'm connecting current to a magnet. So you can create a magnetic field by running a current through a wire. So I'm doing two things. I'm creating a magnet, and then I'm going to run a current through the loop of wire in the armature. So this is the armature. So I'm going to run a current through the loop of wire here, but then there's loops of wire here to produce the magnetic field. So when I turn this on, can you see it spinning?
Yeah.
Okay. And so I have my motor working. It's running on 5 volts. Okay. So you guys are going to create a motor that runs on 3 volts or less. Hopefully. So what happens is, and there's a split ring at the top here. So let me take this apart. I'm going to do it again. Sorry. Let me take, these are the brushes. They make the electrical contact. But I don't know if you can see, can you see the split ring? The splitting?
Yeah.
Okay. So that's used to change the direction of the current. So when the torque, hold on a second, let me put these back in. When the torque on the loop of wire is 0, that's when you change the direction of the current. Okay, you change the direction of the current when the torque on the loop of wire is 0. So it's important how your commutator is oriented relative to your armature. Because if you have it off by 90 degrees, it ain't going to work. Okay. So when you build a motor, anytime you build a motor, you want to make sure that the commutator is the current changes direction when there's no torque on the motor, because you don't want it to change direction when you have full torque. Okay. Any questions on this motor?
What's the handle for?
Oh, good. Yeah. Why do I want to do this? Well, remember what I said is that a motor is a generator running backwards.
Oh yeah.
So I can generate electricity. So what I can do is I need an electromagnet. So I do have to power the magnet in the front. So I do have to power this magnet down here. Okay, so I do have to power this magnet. And then when I rotate the coil of wire, this is chapter 31, in a magnetic field, I can generate a voltage. But in order for you to see this, I have to bring a giant multimeter where the needle goes, you can see the needle go back and forth. I don't know if I'm going to bring that. That thing weighs a ton. I have to go to campus and bring it, but if I can, I'll bring it. It just that the multimeter that I have for this just weighs a ton. It's like from the 1930s. So I have some links regarding the electric motor. I put some there's some links. I hope the hyperphysics one is a good one. I got to double check this second link, but there's a lot of information online showing you how the motor works. If you guys were in class, it'd be much easier to see what I was doing. It's unfortunate because it's nice to see how the commutator works, but you're going to get a great experience building the motor. The instructions for building the motor are really easy. You just need nails, a board. Let me see if I have the kit with me. Your motor kit, basically, and I'm getting ahead of myself. I want to talk about this next week. But this is essentially your motor kit that came with your lab kit. It just has nails, the board, there's a magnet in there. The most expensive part is the magnet wire. So you do have to be careful in building the electric motor because the magnet, you can't waste magnet wire because it's really expensive and hard to get. So we'll talk about that some more next week. But do you have any questions regarding torque and the DC motor? By the way, this device also works as an AC motor. This device also works as an AC motor because I just have to move the brushes. If I move the brushes, then I can use AC current to power this thing. So when I hook up the brushes like this, I don't know if you can see that, then it runs as an AC motor. And maybe Monday, I'm sorry, Friday, I might say something about the Hall effect very quickly. I'm essentially done with the chapter. Questions? No questions? Concerns? Anything? I started grading the exam for the other class, so I'll try to get your exams graded by Friday. There's less of your exams in the other class, but unfortunately, when I grade exams, on paper, it goes much faster. When I grade on the computer, it takes forever, just because everything is slower online. So, no
Are
questions.
the exams good?
Yeah, I mean, I looked through them. They looked okay. I mean, I think for
Apparently,
you
number
guys, it
4
looked
was
okay.
really hard for the other class.
I'm
That's what I
sorry?
heard. I heard that number 4 was really hard for the other class.
Yeah, it really wasn't. I mean, yeah, it looked hard. I couldn't think of one like that for you guys. But your last problem was basically the last homework problem.
Yeah, that it was. Well, it was the lab, isn't it? Basically.
It was a lab, essentially.
Yeah.
But just hidden in terms of an application. But I mean, that exam problem was really, was a lot less work than yours. The one on the other exam, the last problem, was a lot less work on it than what you guys had to do.
Huh.
You just had to see the physics. That's the only thing. Because that one was just Ohm's law and V equals IR. That was it. Like I said, sometimes it's hard to see the physics. That's part of learning physics, right? Especially as an engineer, because if you can see how you can apply the ideas, you can be very clever, and you can be a really good engineer. So that's something that takes a while. It takes experience, I guess, to learn. But so if you guys don't have any more questions, I guess I'm done.
Just on the worksheet,
Yes.
it's basically just each, like A through D is just integrating the cross product on each side of the loop.
Yeah. As long if I can't remember off the top of my head. For the ones where the magnetic field varies, yeah, you have to do an integration. There might be one part where you might not need to do an integration. I forget.
Yeah, it would just depend on if it changed over the, yeah, that makes sense.
Yeah. But yeah, think of doing the integral, but if the field's constant over the length of the wire, then you don't have to do the integral. Because I think I have you do it over the 4 segments, and then in some cases it varies, in some cases it doesn't.
Right, just a matter of if it has that, right, yeah.
Yeah. So it just gives you a good practice problem like that.
That's not due for like a week and a half, though, right?
It's doing the 26th, it's actually next Monday.
Oh, okay. So about a week then.
Yeah. And it shouldn't take too long to do. I mean, it's like the capacitor worksheet. So, and then I have after that, I just have one more worksheet. And I apologize. I noticed I didn't grade the Gauss's law worksheet. I apologize. I didn't see that till yesterday, a couple days ago. I'll get that graded. Okay, so I guess we're done. Unless you have any other questions.
That's it from me.
All right, we'll see you. See you on
See ya.
either an office